Hello everyone and welcome to another video. This is the Physics Junction with Mohammed Talha, and as a part of our AS yearly past papers routine, we're looking at Summit 24 paper 22. Let's get right into it. Question number 1. The list below shows some SI quantities. Underline the quantity that is not an SI based quantity. Current is, length is, time is. Charge is not, because charge is given as the product of current and time. So this is not a base quantity. A square solar panel with sides of length 1300 millimeters. So this would mean 1.3 meters is shown in 1.1. Light is incident normally on the solar panel. This is a square. Power of light incident is 750 watts, and you are asked to calculate the intensity, right? So intensity is power per unit area. That's how it's defined. So power is 750 and the area is going to be 1.3 times 1.3, which is 1.3 squared, and this turns out to be 440 watts per meter square. Percentage uncertainty in the incident power is given, uncertainty in the length is given, and you are asked to find the percentage uncertainty in the intensity of light. So I can see that percentage uncertainty in I would be percentage uncertainty in P plus the percentage uncertainty in A, because this was calculated by having P divided by A. And then A is in itself basically the square of L. So then the percentage uncertainty in A is actually twice the percentage uncertainty in L. So the percentage uncertainty in P is 3. The absolute uncertainty is given here, which is 5 mm. So 3 plus 2 times, so the length of each side was 1300, so 5 over 1300, and then to convert this to a percentage you have 100 here. So these cancel out, so this becomes 2 times 5 over 13, so 3 plus 10 over 13, which is 3.769, or I can say to 1 SF, because that's how we usually give our percentage uncertainties. That's 4%. But even if you write this to 2 or 3 SF, the examiner would accept this. Let's look at the next part now. Useful output of the solar panel is given. We know the input and we are asked to find the percentage efficiency. So efficiency is output over input times 100. To express this as a percentage, output is 160. Let's scroll up to see what the input was. So the input was 750, and then you multiply this by 100. So this turns out to be 21%. Next, another square solar panel is placed so that light of the same intensity is incident normally on it. So what this means is that the input power is going to change because the intensity is the same, because this one has shorter sides than the original panel, right? So if I think about the intensity, which is power over area, so intensity is the same, right? And the new panel has shorter sides, so the area goes down. So I can say that because intensity is constant, basically power is proportional to area. So if area goes down, then the input power is also going down, right? And it has the same power output, and we have to comment on the efficiency, right? So efficiency is output over input. So input is going down. As a result, efficiency is going to go up. So efficiency is going to be greater, right? Now I'll explain this in words. So I'll say that the area of the new panel is less, since intensity is constant. This means that power input decreases, or input power decreases, and this causes efficiency to increase. That was the first question. Let's go on to more of these. Question number 2. A skydiver jumps from an aircraft at time t equals to 0, falls vertically downwards. Variation with t of her velocity v is shown. Okay, so also with questions related to graphs, it often helps you, especially in questions related to momentum or maybe forces, that if you figure out the sign convention, right? Now, if you look at the basically the prompt of this question, so this is falling vertically downwards from the get-go. And all of these velocities are positive, so this means that the examiner has taken this sign convention that downwards is positive in this case. So the variation of velocity is shown. Using 2.1 state the terminal velocity of the skydiver. So the terminal velocity is this constant velocity that it reaches, right? So that looks like 39 meters per second. So the terminal velocity is 39. By drawing a suitable line on 2.1, determine the acceleration of the skydiver at time t equals to 9 seconds. Okay, so 9 seconds, so this must be 7.5, right, in the middle of 5 and 10. So let's figure out where 9 seconds would be. So 9 seconds is going to be here. And basically to find the acceleration at this point, I need the gradient at this point, for which I will need to make the tangent. So I'm using this property that the gradient of the velocity time graph is acceleration. Now I just need to place that line, and this is a bit more difficult to do on the iPad versus how it is on the paper. So I'll just try my best here. Try to make a reasonably long line. So probably something like this is what we should end up with. And now we need to find the acceleration. So we just need like 2 points on this tangent. One of these can obviously be this one right here, which is 9,35. And then I need another one, right? For the other one, let's pick up this one. So the y coordinate is 43. And let's see what the x coordinate is. So that's right in the middle, that's 17.5, 43. Right, and then I just need to use the gradient formula y2 minus y1 over x2 minus x1. So let's try to do that now. So first of all, I'll just explain my reasoning that the gradient is the acceleration at this time, and then for my points, so my points are 43 minus 35, y2 minus y1. So 43 minus 35, y2 minus y1 over 17.5 minus 9. So this turns out to be 0.9411, so 0.94 meter per second square to 2SF. Next, mass of the skydiver and her equipment is 68 kg. Upthrust on the skydiver is negligible. After reaching terminal velocity, the skydiver opens a parachute at time t1. A total drag force of 1800 Newton acts on the skydiver. So it's obvious, if you've read terminal velocity well, particularly the case of the falling parachutist, then you know that when the parachute is opened, the air resistance increases to a very large value, so much so that it's even greater than the weight. So if I just talk about this, I'll know that the air resistance is a lot, which is 1800 newtons, and the weight, which would be 68 times 9.81, is relatively less. Now because this force is much more than this one, so that means the resultant force would be upwards, which means that the resultant acceleration, okay, so the resultant force is upwards, and hence the acceleration is also upwards. So let me just first write that. And then I'll start using Newton's second law, F equals to ma. So I'll know that it's going to be 1800 minus 68 times 9.81. That is equal to MA. So that is equal to 68A. Then you just plug in your values and try to find this out. So that turns out to be 17 meters per second square. I'm not writing the negative sign. You might want to write the negative sign. That's fine. The examiner won't penalize or give you extra credit if you write it or if you don't. Doesn't make a difference as long as you understand the direction. Next, the parachute is fully open at time t2. At a later time t3, the skydiver reaches a constant velocity of 5.7 meters per second. Again, even before reading the question, let me just talk about how this is reached. So as the parachute is decelerates, because acceleration is upwards, velocity is downwards, so it's going to decelerate. So the air resistance also keeps decreasing, and as the air resistance then at that lower value, when it again gets equal to the weight, that's when it reaches its second lower terminal velocity. So you have to describe and explain the variation with time of the magnitude of acceleration between T2 and T3. So T2 was the time when the parachute was opened, right? Okay, no, that's T1. So the parachute is opened at T1. T2 is when the parachute is fully open. And then T3 is when the second lower terminal velocity is reached. So I have to explain the variation with magnitude, with time of the magnitude of our acceleration. So I'll say that as speed decreases, air resistance, or you can say the drag, also decreases, because that's the term the examiner has used. So drag force also decreases. And as the drag force decreases, so that means that the resultant force also decreases, right? Because the drag force was upwards and the weight is downwards. So as the drag force reduces, the resultant force, and hence acceleration decreases. So acceleration also decreases because of the same reason. Then it says calculate the change in momentum of the skydiver between T1 and T3, right? So we know the speed at T1, we know the speed at T3, and if I need to find the change in momentum here, sign convention would not be used because there's no change in direction. In both of the cases, the object was just falling down. So the mass of the skydiver is 68, and initially the speed was 39, right? So it's at T1, and then it's 5.7 afterwards. So PF would be 68 times 5.7 mv, right? Mass times final velocity minus 68 times 39, which is the initial velocity. So this turns out to be negative 2300 Newton second corrected to SF. Let's go on. Lightning occurs when charge builds up in the atmosphere, creating a potential difference between the ground and the atmosphere. During a lightning strike, there is an average current of this much flowing for a time of this much. Calculate the charge transferred. So the equation is Q equals to I T. More specifically, it's delta Q equals to I delta T. But you get the drift. So I is 3.3 into 10 to the 4. T is 2.6 into 10 to the negative 5. So if you work this out, the charge turns out to be 0.86 coulombs. Potential difference is given. You have to find the average power transferred during the lightning strike. A couple of ways you can go about this. You can use P equals to VI, right? And you could have also used the definition of the potential difference in a way. So you could have also used that, but I think this is pretty straightforward. So V is 3 into 10 to the 7. Current is 3.3 into 10 to the 4. You just multiply both of these. So that turns out to be 9.9 into 10 to the 11 watts. Giga is into 10 to the 9, so you divide this by 10 to the 9 and write this as giga. So that's basically going to leave out 10 to the 2, which is 990 gigawatts. A lightning rod is attached to a tall building to conduct charge safely to the ground. Lightning rod is modeled as a uniform cylindrical copper cable of total length 95 meters that runs from the ground to the top as shown. Resistance is given, resistivity is given, and we are asked for the radius. So R equals to rho L over A. A is basically the cross-sectional area, which is pi r square. So R is then rho L over pi capital R under the root. So rho is 1.7 into 10 to the negative 8. Length was 95 meters. Pi is pi. And R is 9.6. And then you have to take the square root of this as well. So this turns out to be, okay, so the square root is on all of this. 2.3 into 10 to the negative 4 meters. Next part, the radius of the copper lightning rod is doubled with no change to its length. Right, so length stays the same, and if radius is doubled, then I can say area goes up by a factor of 4. So resistance is inversely proportional to area. So resistance becomes 1/4 of its initial value. Right, if it asks me to state what it would be, I can also do that because I know it's 9.6. So it would just be 9.6 divided by 4. But the question just said state the effect of this. A section of the lightning rod is has length 0.12 meters, removed for testing. Tensile stress is this much. Section of the rod obeys Hooke's law. Young modulus is given, and we are asked the extension of the section. Right, so first of all, we'll just write down the formula. E equals FL over AX. Now what was given here is that we have the length, we know the Young modulus, and we are asked for the extension, and instead of force and area, the stress is given, so we have this entire thing, right? So F over A is stress, length over extension. I need extension, so that's stress length over Young modulus. Stress is 1.9 into 10 to the 6. Length is 0.12. Young modulus is 1.3 into 10 to the 11. So then this is just a matter of plugging in the values and solving. So then the extension turns out to be 1.8 into 10 to the negative 6 meters. So far, so good. Let's go on to question number 4. A pinball machine uses a spring to launch a small metal ball of this mass up a ramp. The spring is compressed by this much and is held in equilibrium as shown in 4.1. Ramp is at an angle of 15 degrees to the horizontal. Spring obeys Hooke's law and has a spring constant of 29 Newton per meter. Calculate the elastic potential energy in the compressed spring. So we have K, and we also know the compression or the extension. So I can use half kx square for this. So the energy is half kx square. So half k is 29 in the extension or the compression. That is 8 into 10 to the negative 2 squared. So this turns out to be 9.3 into 10 to the negative 2 joules. Next, the spring is released and expands quickly back to its original length. Calculate the increase in GP of the ball when the spring returns to its original length. Okay, so it's not really related to this part, because if it were, then the question would be something like this, that find the height that it gains, given that all of this turns into this. But this is not what it's about. So maybe I can predict that in one of the later parts, maybe the examiner makes me find the efficiency, right? And this is good stuff to be thinking about beforehand, before the question actually is posed. So you need to find the increase in GPE. So the GPE formula is this: delta EP is mg delta h. So delta h is the height that it gains. So for the height, it's compressed by this much, right? So okay, so this is just the GP that it gains as the spring basically decompresses, right? So the spring returns to its original length. So this is that slanted distance, but it's not really the height. The height would be this distance. This one would be cos, so this one is sine. So 8 into 10 to the negative 2 into sine 15 is the height. This is the mass. So 4.5 into 10 to the negative 2 into 9.81 into 8.0 into 10 to the negative 2 sine 15. This turns out to be 9.1 into 10 to the negative 3 joules, right? So out of the elastic potential energy, only this much goes into GPE, which is a really small fraction. The ball leaves the spring when the spring reaches its original length. Assume that all the elastic potential energy is transferred to the ball. Calculate the speed of the ball as it leaves the spring. Again, if you were thinking about what you were doing, then you know that out of the elastic potential energy, only a small portion goes into the GPE. So the rest must go into the kinetic energy. So this being my initial energy, if only this much is going into GPE, so the rest must be going into kinetic energy. So that becomes 9.3 into 10 to the negative 2 minus 9.1 into 10 to the negative 3. This is basically the kinetic energy, and that is equal to half mv square. Mass was also given. So mass is okay, and also it's better, I forgot to do this in a hurry, but it's better that you always write the kinetic energy formula first, or any other formula first, to score partial credit where you can. So this is half, and mass was 4.5 into 10 to the negative 2 into v squared. From here you just cross multiply and find v, which turns out to be 1.9 meters per second. Ball comes to rest on a horizontal trapdoor of negligible mass at a distance d from its pivot. A force F acts vertically downwards a distance of 2 centimeters from the pivot. This being the pivot, this is that force, as shown in 4.2. And when it's at rest, so basically it's this weight of the ball which would be acting. I just use the mass, which was 4.5 into 10 to the negative 2, and I'll just multiply this by 9.81 to get the weight, which is the force. The trapdoor is in equilibrium when F is 1.7, calculate D. So if it's in equilibrium, this means that I can use the principle of moments. So I'll just say that F, the force, times 2 centimeters. So F times 2 equals 4.5 into 10 to the negative 2 times 9.81. This is all the force multiplied by D. But keep in mind that because this was in centimeters, D would also be in centimeters. So D from here turns out to be 7.7, right? When you substitute F as 1.7. So D turns out to be 7.7, and in meters this would be 7.7 into 10 to the negative 2, because this is centimeters. Force F is decreased from 1.7. State the direction of the resultant moment about the pivot on the trapdoor. So F was previously producing an anti-clockwise moment, so anti-clockwise moment goes down, clockwise moment is more, so it must rotate clockwise. Let's move on to the next question. 5 part A, state Kirchhoff's second law. So Kirchhoff's second law, Kirchhoff's first law, again you have like most of the other definitions that you have or the statements that you have. It comprises of two important parts. So Kirchhoff's second law is the voltage law. So you say sum of EMFs, electromotive force, equals sum of potential differences or potential drops for a closed loop. This is what you have to say. So for a closed loop. If you miss out on saying the closed loop, you will not get the mark here. A battery of EMF 9 volts and negligible internal resistance is connected in series with a variable resistor and a thermistor Y. So this is basically making up a potential divider. 5.2 shows the relationship between temperature and resistance for the thermistor. Always make sure to note the multiples if any, or the prefixes if any, but there are none here. Current in the circuit is given, potential difference across Y is given, and we have to find the resistance of X. So if the potential difference across Y is 4, so by KVL, basically I know that the other 5, 9 minus 4, 5 must be appearing across X. And I know the current through the circuit, which is going to be the same for either the source or Y or X, because this is a series circuit. So then if I just need to find the resistance, I can use V over I. So resistance is V over I, which is 5, 9 minus 4 over 1.1 into 10 to the negative 2. So this turns out to be 450 ohm, correct to 2SF. Temperature of Y is changed, the resistance of X remains unchanged. Determine the new potential difference across Y. Alright. So temperature of Y is now 190, right? So we don't know the older temperature. We just know that now the temperature is 190. So 190 must be this. Okay, so 190 is the new temperature, right? So 190 is here. So this is 190, right? This is 190. So if I read this off, this means that the resistance of the thermistor is 25 ohms. So that's Y, right? So resistance of Y is 25 ohms from the graph. And I need the potential difference across Y. Alright, so potential difference across Y, I can just use voltage division. So I can say the voltage across Y, if I set up the expression for that, 25 in the numerator. In the denominator, the sum of the resistances, 25 plus 450 times the EMF, which was 9, and you just find this out. So this turns out to be 0.47 volts. Okay, next part, resistance of X is increased. Temperature of Y remains at 190. By reference to the current in the circuit, state and explain the effect of this change, if any, on the potential difference across Y. So if this is with reference to current, so you can't use potential difference arguments, you have to then talk about the current. So what you'll say is this, that if the resistance of X is increased, you'll say that total resistance increases, causing current in the circuit to decrease. Alright, and now you have to talk about the potential difference across Y. So yeah, for Y, if you're talking about a thermistor, its resistance is constant because temperature is constant. So you'll just say that as the current decreases, the potential difference across Y also decreases, right? So in this case, what made this question slightly weird, you might call it, is usually we are used to using V equals to IR for the other resistor, the one which is not the thermistor or not the LDR. But the catch here was that since this is at a constant temperature, so I can use V equals to IR for this one. I can't use V equals to IR for this one, because for this one, the thing which is important to note is that its resistance goes up and current goes down. So overall, I don't know what's going to happen to its voltage. Would it increase or would it decrease, right? But because its resistance is constant, so resistance is constant for that, current goes down, so potential difference or potential drop also goes down. Let's look at this question. Light of a single frequency is incident normally on a diffraction grating. Interference pattern of bright and dark fringes form on the semicircular screen in 6.1. Wavelength is given, separation of lines is given, and you have to find the total number of bright fringes formed on the screen. Again, for anybody who has been practicing diffraction grating well, they know how to do this question, because all right, it's something that doesn't really appear a lot in paper 2, but it does appear very frequently in paper 1 in MCQs. So first let's figure out the order of the bright fringe. So if I talk about the bright fringes, I'll assume that all right, the last fringe, if it were to form, it would form here, right? And if this is my central maxima, I know angles are to be measured from here, so this is 90, right? So this is my n equals to 0, my central. So theta is 90, so then this becomes n lambda equals to d, or n equals to d over lambda. So d is 3.8 into 10 to the negative 6. Lambda is 520 into 10 to the negative 9. If you work this out, this turns out to be 7.3. Even if this was 7.999, I would round this down to make it 7. Because what I'm really saying is that the 7.3 maxima occurs here, but we know that's not possible. It's either going to be the 7th, which might be somewhere here, and the 8th would obviously not be detected, right? So it's 7. We always round down with the order of the maxima. So this is 7, but there are going to be 7 on either side and the 1 in the center. So this becomes 2 times 7 on either side plus 1 in the center, and this is 15 here. The light is replaced with red light of a single frequency. State whether the frequency of red light is greater than, less than, or the same as the frequency of the original light. So red light has the greatest wavelength of them all, so it has the least frequency of those. So I'll say that the frequency of red light is less, right? Frequency is less, wavelength is more. State and explain the effect of this change on the number of bright fringes formed. A calculation is not required. So I'll just write down the diffraction grating equation again. N lambda equals to d sine theta. Lambda goes up, so the angle of a certain order, of any specific order, that would go up, and that would obviously mean that less fringes can now be captured on the screen. So you'll have less fringes forming. So you'll say that the increase in wavelength causes an increase in the angle for all orders allowing less maxima to be seen. So it says bright fringes, right? So let's use the same terms. Less bright fringes to be seen. Let's go on. A particle Q and a particle R are composed of one quark and one anti-quark. So we know these are called mesons, and that's what the question is. So these are mesons, and that falls under the major category of hadrons, right? So anything that's made up of quarks is hadrons, and then something which is made up of 3 quarks is called baryons, and then the other one, which is a quark and an anti-quark, that's what our syllabus restricts us to. That's a meson. Q has a charge of -1e, where E is the elementary charge. R has a charge of 0. Complete 7.1 to show a possible second quark in each of Q and R. So you remember that U, C, T, all of these are +2 by 3e, right? And then the other ones, which is opposites or down, ups or down, charmed, so strange, topped, so bottom, these are -1 by 3e, and then their anti-quarks obviously have the same but opposite charge. So if this is strange, which means it's -1 by 3, so it needs a -2 by 3 to make it -1, right? So it must be anti-up or anti-charm or anti-top. So any one of these work. This is anti-up, right? So it is -2 by 3e, so I need a +2 by 3e to basically nullify that, right? But it can't be the same one. That's just the only restriction. So there's an anti-quark and there's a different quark with mesons. So it could be either charm or top. All right. So in this mark scheme, the examiner was accepting up as well, but technically it cannot be correct. So it's better to be safer and write any of the other two options. So that wraps up this paper. I hope that this clarifies the paper solving, and we got done in like pretty good time with this. So that's it for this video. Like this video, comment if you have some suggestions or improvements, share this with your friends, and do subscribe to the channel, because a lot more content like this, which is going to help you ace your exams, is going to drop in the days to come. See you in the next one.